All right, now that we've taken a break, let's go back and look at the algorithm for learning the Q function. In the previous lecture, we saw that if we can figure out the Q function, it's going to tell us exactly where to go to get the optimal policy. So as a review or a reminder, if you're in state SI, take an action AI, the agent is going to end up in a new state SI plus 1. And then out of that new state, you can choose a bunch of different actions, AI plus 1, coming out of that. And in fact, this is key to learning the Q function. Remember, the new state is based on the old state plus the action. So by definition, we defined Q last time. Q at the current state associated with this particular action is you look at the action and the state and you get a local reward. And then in the next state, the SI plus 1 state, you grab the V function associated with the optimal policy pi star. So you take any action, optimal or non, out of SI, you get the local reward, but then you say, okay, I'm going to go optimal from then on. And from the previous lecture, we saw that you can calculate the optimal V value in that next state by looking at all actions out of that next state. So that's all of these actions we were indicating here. All of those actions, and you collect the local reward going forward one more step, and then you say, let's grab the optimal V for one step ahead of that. So we go one step forward with the Q, collect the reward, and then optimal from then on, but then this optimal policy V function in the SI plus 1 state we can get by looking at all possible ways out of that next state and collecting rewards and adding up the total discounted reward here. And in fact, this thing inside the brackets, by definition of Q, is in fact Q of SI plus 1, AI plus 1. So that is the Q at the next state. So what that means is that the Q at our current state associated with some action A can be calculated as R, the local reward going forward one step, plus gamma times the maximum of all of the Q's going out of that next state. So in fact, even though this is kind of complicated, collecting all this together, this is really easy to implement, is that if you want to calculate a Q for a current state, you go forward one step, collect the reward, and then you look at all possible ways out of that next state and find the maximum Q going out of there. And that's going to give you the optimal. Of course, this is totally dependent upon whether the Q in that next state is correct or not. So in fact, this becomes an iterative process where you can initialize the Q's, and then you just keep running this algorithm on all the states, and the Q's keep updating themselves. And so it truly is a learning algorithm because it's learning based on the rewards coming in locally. So it allows an incremental step-by-step learning of not Q, but Q hat. It's an approximation because you never really get the exact Q because we just keep updating. Just like with a neural net, you keep updating, the RMS goes down, but it never gets perfect. With this algorithm, notice in this formula, there are no V's, there are no pi stars, there's no delta. All there is the rewards that get collected from the environment. So you don't need any kind of policy, you don't need a V function. All you need is collecting rewards, and you don't need a state model of the system. All you need to do is interact with the environment, go forward, try possible routes out of the next state, and you're good. Okay, so here's the algorithm. First thing to do is initialize Q hat. It's like initializing the weights of a neural net. You can randomize these numbers. Or if you have some knowledge about what are good or bad moves within the system, you can a priori stick those in. And so, for example, if you're playing a game, and you know some good strategies based on certain states, you can pre-program those into the queue function. Step 1, you pick a starting state S0 anywhere within the state space. So for the grid world, you just pick some spot. You observe the current state, and we're going to do this starting with S0, and then we keep moving forward. Observe the state, choose an action, and in fact, you don't necessarily need to choose the best action based on the queues you know right now, because the queues were initialized randomly. So you take an action and you get a reward. So notice the reward comes from what state we're in and what action we chose. So from the environment, you get a reward and a new state, Si plus 1. And then we look at that new state, and we look at all of the ways out of that new state, and we pick the maximum queue in that next state, and then add in the local reward that we got when we took that first step. So it's taking baby steps through the system. You get local reward information, and then you pull up queue information for the next state. Whether this works or not depends greatly on good reward structure. Well, that makes sense. If the rewards are bogus, it won't know what's good and bad. Eventually, you have to get to the goal. So if you keep choosing random actions and you never get to the goal, you'll never get the reward. Starting states are critical. You've got to visit a lot of different states in the state space. And the exploration strategy, meaning when you're in a state, what action do you take? If you always choose the optimal state, the optimal action coming out of your state, SI, you won't necessarily explore a lot of paths, because remember, these queues were initially random, and so they don't contain maybe any information about what's good or bad. So if you keep choosing the best of bogus information, you may not explore the actual best path. So there's methods we'll talk about where you randomly select these exploration states that you go forward to. All right, so we're going to go back to our grid world example, and we're going to initialize the queue values. So this is a table of queue values here. Don't confuse these with rewards, or don't confuse them with the V functions. These are queue values, and just to show you how this works, all of the queues are set to 10. And then we'll see, well, how does this algorithm improve on the values that we've just randomly chosen? Even the ones going into the goal, although we might know ahead of time we'd want to make these bigger, we're just going to make everything 10. And then we have to remember what the R values are for our grid world, and that comes from the previous lecture, previous example. 2 lectures ago, actually. Remember, the rewards are 0 everywhere except when you go into the goal. And so you can see how important this is, because it's going to tell the queue function going into the goal gives you the big reward of 100. All right, so the strategy I'm going to show you initially is we're going to work our way outward from the goal. You don't have to do that. It just makes it faster to see how this thing works. We could pick state 2 and work from there, and then pick state 1, and then state 4, and state 3, state 5, but we're going to start with 5. So remember, the queues are these numbers, and so we're going to start state 5, and then we're going to say, well, let's go from 5 to the goal. That's one of the actions that we need to update our queue function. And so if you go to the goal, you get the reward of 100 from over here, remember. And then the algorithm says, okay, now you're in the goal, and so look at all of the possible ways out of the goal where there are none, and so you get 0 here, and so the queue function then becomes 100. So this arrow, if we were doing this in class, I'd update this. There's not really a lot of room, but we'd write 100 on this one here. Okay, if you're still in state 5, but you go to 3, so we're taking this action, we get a reward of 0. And then we're in state 3, so we look at all of the queue values going out of state 3, Well, if you go up, Q is 10. If you go left, Q is 10. If you go right, Q is 10. So it's the maximum of all those 10s multiplied by gamma of 0.9. And so you get a 9 for this Q value. So if I can write it in here, the Q value now changes from 10 to 9. All right, now we're going to say, well, let's be in state 4. And if you go to the goal, you get the local reward of 100. And then there's nowhere to go, so the maximum Q out of there is 0. So that Q value becomes 100. So this is 100 here. Much better 100 that time. Give me a round of applause, please. And then if you're in state 4 and you go to 3, you go down, so the reward is 0. And then you look at all the possible ways to go out of 3. Well, it's still 10, 10, 10. The maximum is 10 multiplied by 0.9. And so going from 4 to 3, now this Q value changes to a 9. And the same thing for from 4 to 2. Same process, the reward 0, maximum of all the ways to go out of 2. And so this changes to a 9 here. That's the from 4 to 2. You keep doing that. Now we go to state 3. Okay, we're starting in state 3. We go from 3 to 5. The reward for doing that is 0. That's this reward here. But now we're in state 5, and we have to look not at the original states in 5, or Q values in 5, but we have to look at the new updated values that we calculated here and that we copied somewhat blurrily up here. So that means that we have to find the maximum. Once we're in 5, we have to look at all the ways out of 5, so it's the max of those. So we get 90 for that, and so we would write that up here going from 3 to 5. So this is now a 90 here. Not so great. And then if you go from 3 to 1, you're going this direction here. The reward is 0, and then you're in 1, so the two ways out of 1 are 10 and 10, so you update that. And so here, this Q value, instead of being 10, now goes to a 9. Then we go to state 2 and state 1, repeat the same process. 2, we'd look at going from 2 to 4, collect a reward of 0, and then we'd look at the different Q's going out of there, which is 100, 9, and 9. So we find the maximum of 109 and 9 times 0.9, and we get 90. And so the Q value for that is 90. So that's going from 2 to 4. So this arrow changes to a 90. And I'm going to quit writing up here. I'm going to show you later on what these numbers are, because it's getting kind of messy. But we keep doing that same process. You go from 1 to 2, and then you look at all the ways you go out of 2, and you find the maximum Q, and you get an 81. And then if you go from 1 to 3, and then all the ways out of 3 are 90, 90, and 9, so you get an 81. So all those numbers I was trying to write up there. Here are the Q, here's the Q matrix, or the Q values for each possible action that can happen. So if you go from 2 to 4, that has a Q value of 90. If you go from 5 to the goal, that has a Q value of 100. So already you can start to see that if we start out in 1, we can start to find an optimal path. Looks like it's ambiguous whether we go up this way or this way, because they both give us 81 reward future going forward. But then when you're in 3, you have a choice of going this way for a 90 or this way for a 90. Both are equally good. And then once you're in 4, you don't want to go 9 and 9. You want to go the direction that's going to give you the most future reward, which is 100. Remember, that's what the Q value says. It says, if I'm in this state and I take this action, this is how much reward I'm going to get if I go all the way to the goal. Okay, so we literally picked up the agent every time. We said, okay, we're going to start out in 5, and then we worked that, and then we moved it over to 4. This is optimal if you can start near the goal and pick the agent up, but in many real-world situations, you can't do this. So an alternative, if you can't pick the agent up, is you start, say, at 1, and then you just randomly choose actions going until you hit the goal. That's what we talked about as the exploration strategy. You do that as many times as possible until the queue converges. And in fact, that's what he did when he trained the queue function to play backgammon. Is in a backgammon game, you start at the beginning, and then you make a bunch of moves, and somebody wins and somebody loses, and that's the reward. So you go all the way to the end, and then you update the queue functions as you go along, and assuming that you start out with many different games, that is, you'll always start with the same initial state, but the gameplay can be totally varying because you're going to vary your strategy of what moves you make as you go forward. And of course, the opponent will do the same thing. Another alternative would be you go all the way from one to the goal, but you don't update the queues as you go along. You simply wait till you hit the goal, and then you work your way backward, which can speed things up as well. All right, so here's our queue values after one epoch, that is one pass through training all of the different states and actions. So if we do it again, we're going to use, sorry for the scrolling, we're going to use all of these queue values now to update again. Again, this is an iterative process. This is not the final answer. This is just one step toward the final queue values. So again, if we're in 5 and we go from 5 to the goal, we get the local reward, and we still look inside the goal. We can't go anywhere, so the queue doesn't change. We go from 5 to 3, the local reward is 0, but now if you look at state 3 up here, the ways you can go out of that are 9, 9, and 90. So that's what we do here. We find the maximum of that, gives us an 81, and we update the queue value. We do that for all of the different actions here and all of the different states. We keep updating, we keep collecting the local reward, and then look at the maximum out of the next state. Local reward, maximum out of the next state, and you keep updating the queue values for state 4, state 3, state 2, and state 1. Again, process, pick a state, pick an action, take the action, get the reward, and then when you're in the next state, look at all of the ways you can go out of there and find the biggest one. After the second epoch, here are the queue values. So this is queue after epoch number 2. It's not converged yet. We could keep doing this for 100 epochs, but it would take a long time. But notice that now, let's say we started in state 2. Which way would we go? We wouldn't go 72 because 90 is a bigger queue value. So we'd end up in state 4. And then we're in state 4. We wouldn't go 81 because 100 is a better queue value, and we'd be at the goal the fastest way. So you can do that from any state, just looking at the queue values going out of each state as you march along. All right, next lecture will be some, I guess, advancements or details about the theory of queue, but this is the example that you'll need to do the homework, and this is the main stuff I want you guys to learn.